Hello, everyone. I am super excited to introduce our champ speaker for this week. We have Amy Huang from Texas A&M, who's going to tell us about tensor ranks and matrix multiplication complexity. Amy.
Thank you for your introduction, and thank you for inviting me to speak here. So today, the part of projects I'm going to talk about is about tensor ranks and matrix multiplication complexity. So in fact, this part of the project is not a very core commutative algebra, but I do have some works that is in core commutative algebra and homological algebra, and I briefly introduced that part in my elevator pitch video. So if you're interested, I will very welcome you to look at that part. But today I'm going to talk about this part of my project that concerns tensors. So the outline is as follows. In the first half of my talk, I'm going to, I know most of you are not familiar with this part, so I'm going to have a brief introduction of what is a tensor and what is a symmetric tensor and what is a rank of a tensor. Then I'm going to talk about what is a border rank of a tensor and other notions of ranks that I will be interested in. Then later, I'm going to talk about what is the popular method of lower bounding those notions of ranks. Then on the last part, I'm going to talk about what we have done, which is we found a connection between the different notions of ranks, the difference between those notions of ranks, and a very well-studied object, which is called polynomials with vanishing Hessian. And on the second part of my talk, I'm going to tell you a little bit about how do we compute the border rank of 3x3 permanent. And so first of all, I'm going to talk about the motivations. How does it relate it to matrix multiplication complexity? Then I'm going to tell you a little bit more about what is known and what is unknown about this tensor and some related tensors. And the last part, I'm going to give you a broad picture of what techniques that we used in computing the border rank. So let me get started. So I will start from a brief introduction to tensor. So when we talk about tensors, tensors has different modes. So if you're looking at a one-mode tensor, that's just a vector. And if we talk about two-mode tensors, that's just a matrix. So it lives in V1 tensor V2. And in this case, tensor rank is the same as matrix rank. And in fact, all the notions of ranks that I'm going to talk about will coincide for two-mode tensors. So, so tensor rank is the smallest R, such that you can write your matrix as a sum of R rank 1 matrices. And for rank 1 matrix, you can always write it as A1 times B1 transpose. So if your tensor has 3 modes, then actually things are more complicated. Here, you can imagine your 3-mode tensor sits in a 3-dimensional array. So it will sit in the space V1 tensor V2 tensor V3. And for rank 1 tensor, this just means that you pick a vector for each of the modes, and then you just tensor them together. So as the picture shows, you pick a vector A1, B1, and C1. Now you can multiply its entries in different positions and form actually 3-dimensional array of numbers. And the tensor rank, similarly, is the smallest R, such that you can decompose your tensor into some of rank 1 tensors. And for higher mode tensors, it will be similar to the 3-mode case. So you'll have an n-dimensional array. And the rank 1 tensor means you pick a vector for each of the mode and tensor them together. And similarly, tensor rank is just the smallest R you can write. You can decompose your tensor into rank 1 tensors. So this tensor decomposition has a lot of applications. I want to briefly say some words about some of them. So for instance, when you're doing high-dimensional data analysis, your data is going to have a lot of attributes. So you can organize your data according to their attributes into a high-dimensional array. So this will form a tensor. So if you want to analyze it, you usually want to find a low-rank decomposition or low-rank approximation of your tensor. And similarly, if you're doing deep learning, especially in unsupervised deep learning, you're given a large set of data and you want to do recognize the patterns in your data. That will also correspond to doing a low rank approximation or low rank decomposition of the corresponding tensor. And also when you're doing PDE, when you want to solve the PDE, sometimes people want to do a dynamic low rank approximation of the solution. And in this case, for a multivariant function, we say that it is of rank 1 if it is separable, and a function is of low rank if it can be write as a sum of small separable functions. Also, when people are doing probability, if you are dealing with joint probability distributions, you can also organize your distribution into a high dimensional array. So it will form a tensor. And if your random variables are independent of each other, then your tensor will have rank 1. However, if your random variables have some correlations, for instance, if you have some hidden variables determining those correlations, you can see that by exploring your tensor that has some low rank decomposition. Also, tensor decomposition has other applications in physics and other areas of science like phylogenetics. And today I'm going to focus on the application on complexity theory and geometry. So the tensors I'm going to look at today will have some extra symmetries. And in fact, I want to look at what's called symmetric tensors. So if your tensors has 2 modes, then symmetric tensor is the same as symmetric matrix. In other words, it means that if you permute the indices of your matrix, then the entry stays the same. So similarly, for 3 modes and higher modes tensors, we say a tensor is symmetric if we can permute the indices and the entry stays the same. And a lot of natural tensors arise as symmetric tensors. For instance, if you take the partial derivative of smooth functions, it will form a symmetric tensor. So if your tensor is symmetric, most of the time we want to find a decomposition that respects the symmetry. In other words, we want to decompose it into rank 1 symmetric tensors. So for rank 1 symmetric tensor, this just means that instead of pick a vector for each of the mode, now I pick the same vector for all of the modes and then tensor them together. And in terms of entries, this means the ijkth entry of your tensor equals vi times vj times vk. And for a symmetric rank decomposition of a symmetric tensor, this just means I want to decompose my tensor into R sums of rank 1 symmetric tensors. So this is the same, a very similar picture as before. The only difference is that in all those rank 1 tensors, now these 3 vectors are in fact the same vector here. So if we want to dealing with asymmetric tensors and symmetric tensor decompositions, in fact, this has a very close relation to an object that we all love, which are homogeneous polynomials. So for a symmetric tensor, it's in fact equivalent to a homogeneous polynomials of degree d. And here d is the number of modes of your tensor. And the number of variables of your polynomial will be the same as dimension of each mode of your tensor. And if you're given a symmetric tensor, I can just give you a homogeneous polynomial. What do I do? So I take each of the entries and I multiply with the independent variables corresponding to the indices of my entries, and then I sum them together. In this way, I will get a homogeneous polynomial, and this will be equivalent to a symmetric tensor. And for symmetric rank 1 tensor, this will be corresponds to the linear powers. So I take a linear form and I raise it to power d. And for symmetric rank decomposition of my tensor, this will correspond to a more familiar object, which is called Warring rank decomposition of a polynomial, which is how do you decompose your polynomial into sum of linear powers. So it turns out that this the space of linear powers and Warring rank decomposition has been very intensely studied in Asian Italian among Asian Italian geometers. And if you look at the space of linear powers, or the space of symmetric rank 1 decompositions. This is completely determined by the linear form. So this space is isomorphic to the whole vector space. And in geometry, we want to deal with compact objects, and all these notions are invariant under scalar multiplication. So we want to think of this space of rank 1 symmetric tensors is isomorphic to projective space, and this sits inside the space of all symmetric tensors. So there's a picture here. The picture I'm looking at is I embed the projective space via the Veronese embedding. So this is what I call X. And this object is, you can think of it as the space of rank 1 symmetric tensors sits inside the whole tensor space. And if you want to draw rank 2 symmetric tensors, or if you want to draw the rank 2 points, so rank 2 points means that it will sit on a secant line of this variety X. So you want to take the union of all secant lines. That will give you the set of all rank 2 points. However, you will have such phenomenon, which is that if you take the limit of a secant line, then you get a tangent line. However, if your tensor has higher modes, usually the points on your tangent line does not sit on any of the secant line. So you get some extra points. So for instance, this point has symmetric rank much higher than 2. However, this is in the limit of a secant line, so it can be approximated arbitrarily close by rank 2 points. So in other words, this is in the limit of rank 2 points, but this has higher rank. So in this case, we want to kind of study these points as a whole. This will give us the definition of what's called a secant variety. And if you want to do a similar thing for rank R points, this is basically what's called the rth secant variety of X. So everything can be generalized to the case where X is a general projective variety. So the rth secant variety of X, basically it's the closure of rank R points. So you take R distinct points on X, and you take the linear span. So this notion is the linear span of R distinct points, and I take the union of all possible linear span, and then I take the Zariski closure. So this is what's called the rth secant variety of X, or the points that can be approximated arbitrarily close by rank R points. So this gives us another definition, which is called border rank. So the border rank of a point is the smallest R such that your point sits in the rth secant variety, or in other words, is the smallest R such that your point sits in the limit of the span of R distinct points. So for instance, for example, if you look at this point in the projective space, so this point in fact has rank D, but it has border rank 2, because you can write your point as the limit of the sum of 2 rank 1 points. So now, so we know that this point has border rank 2 and is in the limit of rank 2 points. However, we can also think of this point has a different rank 2, which is, we can think of this point is in the span of a subscheme of X that has length 2. And the subscheme I'm looking at, it's a point support at this point, which is L1 to the power D, and a tangent direction, which is in the direction of this tangent line. So this is the length 2 subscheme of X I'm looking at. And I can say that this point is in the span of this length 2 subscheme. So this gives us another notion of ranks, which is called cactus rank. So cactus rank of a point is the smallest R such that you can find your point in the span of a subscheme of length R. So now you don't just require R distinct points, you allow arbitrary subschemes of length R. So this will give us what's called the cactus rank. And the smoothbore rank is very similar to cactus rank. The only difference is that now I require that my subscheme is not arbitrary subscheme, but I only allow smoothbore subscheme. In other words, I only allow my subschemes to be the limit of R distinct points. So in other words, this is the smallest r such that your point is inside the span of the limit of r distinct points. So this is what we call the smoothable rank of a point. And now let me recall the definition of rank. So the rank of a point is the smallest r such that f is in the span of a smooth subscheme. So a smooth subscheme of length r basically just means r distinct points. So you only allow smooth subscheme, and you want to find out the smallest length such that f is inside its span. So now if you look at these three different notions of ranks, we can see that the difference is that we restrict ourselves to a smaller and smaller subset of subschemes that we are allowing. So you expect the rank gets larger as you go down. And in fact, this is the case. So you will have your rank is the largest and your cactus rank is the smallest among these three. You also have a relation between smoothable rank and border rank, because you see the smoothable rank is you want to find your point in the span of a limit of r distinct points. However, the border rank is you want to find your point is in the limit of the span of r distinct points. And we know that the limit of the span is always larger than the span of the limit. So the border rank will always be bounded above by the smoothable rank. And now let me get to the main points of the first half. I want to focus on the difference between cactus rank, border rank, and smoothable rank. So before I get to the main material, I want to briefly say something about what's the most subtle part about distinguish these notions of ranks. So the most difficult part of finding out those notions of ranks for specific points is figuring out what's the lower bound of these ranks. So the most popular lower bound method of distinguishing finding out those ranks are, for instance, let me use the border rank as an example. So if I know the defining equation for all secant varieties, then I will know the border rank for all points, because the border rank is testing whether your point is in the secant variety or not. So if I know the equations, I can just plug in my points to the equations. So the easiest case to find the equations is when you look at two-mode tensors, which is just mean matrices. So we know that for a matrix, I want to think of a matrix to be isomorphic if it is only different by change of variable. So in other words, I will have a group which is GLA cross GLB acting on the space of tensors or two-mode tensors or matrices. So it will induce the action on the rth secant variety of the segregate embedding, or you can think of it just induce an action on the space of border rank less than or equal to r tensors. So it will induce the action on the defining equations of this rth secant variety, or the space of polynomials vanishing on this border rank less than or equal to r tensors. And in fact, this is the simplest case. So in fact, the ideal defining the rth secant variety is given by the r plus 1 cross r plus 1 minus of your generic matrix. And as a representation over GLA cross GLB, this is in fact an irreducible representation of GLA cross GLB. So this is basically the easiest possible case for tensors when you try to generalize this procedure to higher mode tensors. Things are starting to get much more complicated. So a very popular way to generalize it is we want to take our space of tensors and then map it to a space of much larger matrices. And we'll say that if my tensor has low rank, then the image in this large matrix will still have low rank. So I can take minors of this large matrix to get equations for secant varieties. So this will give you a lot of equations of different degrees. And this is what's known as Young flattening or causal flattening method. This will give you a lot of extra equations for secant varieties. However, it is known that all these determinantal equations cannot distinguish the previously introduced three notions of ranks. In other words, this will give you exactly the same lower bound for both cactus rank, smoothable rank, and border rank. And this is basically the main reason that it is so difficult to find out all the defining equations for secant varieties, because you can't distinguish those three different notions of ranks. And I want to say that distinguishing between these three notions of ranks is a very subtle problem. And the motivation of our projects actually comes from results several years ago that from Buczynska and Buczynski says that if you look at cubic polynomials for less than or equal to 4 variables, then in fact the smoothbore rank is the same as the border rank. And in the same paper, they gave the first example that you have a gap between the smoothbore rank and border rank. And this is in fact a cubic polynomial in 5 variables. And this polynomial is very special in other contexts. So Ottaviani observed that this is in fact a very classical object, which is called polynomials with vanishing Hessian. So he asked if there's a relation between this very subtle difference between the smoothbore rank and border rank and this very classical object, which is polynomials with vanishing Hessian. So let me recall the definition of polynomials with vanishing Hessian. So this is a very easy to check condition. So this is the same as saying that if you take the Hessian matrix of your polynomial and you take the determinant of your Hessian matrix, you will always get the 0 polynomial. Then we will say that this is a polynomial with vanishing Hessian. So this is very easy to check. So basically, we answered Ottaviani's question in the positive way in certain cases. And the cases that we answered his question is when my polynomial is concise of minimal border rank. So concise is a definition basically saying that even after a linear change of variables, you cannot rewrite your polynomial in fewer variables. And this is also a condition that is very easy to check. And for minimal border rank means this is the smallest possible border rank for concise tensors. So we say that a polynomial is of minimal border rank if the border rank is the same as the number of variables. And if you think of it as a symmetric tensor, this will be the same as the dimension of each mode. And in these cases, so if I'm looking at a concise polynomial of minimal border rank, together, this is joint work with Mateusz and Emmanuelle. So we showed that this condition that vanishing Hessian is equivalent of saying that you have a larger cactus rank than your border rank, and it is equivalent of saying that you have a larger smoothbore rank than your border rank. So basically, let me have a very small sentence about the proof. So for the one side, we use newly developed technique, which is border apolarity, which I'm going to discuss it briefly on my second half. And on the other hand, we basically find a smoothbore subscheme that spans the concise polynomial. And maybe I will remark for my last sentence of my first half, saying that this is in fact the first time that explicit equations are found to distinguish these three notions of ranks. So that will be the first half of my talk. So let me stop a little bit and ask if there's any questions. All right, then let me move on. On the second half of my talk, I want to talk about recent results of how do we compute the border rank of a very specific tensor, which is 3x3 permanent. So let me start with the motivation of this problem. So this all starts from a question in computer science community of how do you do fast matrix multiplication of a very large, of two very large square matrix. So naively, you need n-cube scalar multiplications in order to multiply two n by n matrices together. However, the first breakthrough is there's an algorithm called Strasson's algorithm. This is an algorithm that explicitly gives you a way of multiplying two by two matrices using 7 scalar multiplications instead of 8 scalar multiplications. So it can be explicitly written down. So now this can be generalized to large matrix because you can always break your large matrix into 2 by 2 blocks and then just apply Strasson's algorithm there. So this will give you the result that we only need n to the power log 2 of 7, which is approximately 2.81. that many scalar multiplications in order to multiply two large square matrices together. So it turns out that this problem has a lot, is very closely related to the border rank of a very specific tensors, which is called matrix multiplication tensor. So a matrix multiplication tensor is a three-mode tensor. And if you think of it as a multilinear map from the first two modes to the last mode, then this multilinear map is just given by matrix multiplication. And also, if we only want to consider square matrix multiplication, then sometimes we just abbreviate by keep track of the size of the square matrix. So how does it relate it to this fast matrix multiplication? Because we can quantify how fast we can multiply two matrices by computing what's called the exponent of matrix multiplication. So this is usually called omega, and this is defined to be the exponent in n. That is a unit big O of that many arithmetic operations in order to multiply two large square matrices together. And this is also the same as the exponent in n, such that this is approximately the border rank of a very large square matrix multiplication tensor. So in fact, there's a very astounding conjecture in the community, in the computer science community, is that in fact this exponent is 2 instead of. So if you think about it, if you want to add two large square matrices together, you need at least n squared and many arithmetic operations. So now this conjecture basically says that, oh, if you only want to do it asymptotically, in fact, multiplying two large square matrices is kind of the same complexity as adding two of them. So this is very surprising. But in fact, there's a lot of progress towards this conjecture. So let me tell you some of it. So this is what's the history of the estimates for this exponent. So the naive bound is 3. So as I explained, Strasson's algorithm, which use how to fast multiplying two by two matrices together, gives you the upper bound of log 2 of 7, so 2.81. Then the next breakthrough is what's called asymptotic sum inequality, and it's given by Schohager. It's in 1981. And I'm not going to tell you the details about the technique, but I just want to say that all these 4 results are using this asymptotic sum inequality. And the latest development and the next breakthrough is what's called the laser method. And this is also given by Strasson in 1986. And so I'm also not going to talk about the details of the laser method. It's pretty complicated, but briefly speaking, it's using a sequence of auxiliary tensors, and you want to take an auxiliary tensor and take a high Kronecker power of an auxiliary tensor and do some degeneration. And you want to estimate the border rank of this high Kronecker power in order to get a good upper bound of omega. So I probably would just say that, in fact, all these results, including the current best results, are given using Strasson's laser method. And what's more surprising is that starting from 1987, all these results until the best one today are all using the same auxiliary tensor. And they are all using what's called a big Coppersmith-Winograd tensor as an auxiliary tensor for the laser method. However, there's some not that good news about this auxiliary tensor. It's Legall in 2014 discovered that there is a barrier that you can never use this big Coppersmith-Winograd tensor and use a laser method to show that omega is less than 2.37. So, but that's not the end of the story, because now, although we know that the big Coppersmith-Winograd tensor is not that good, maybe we can find some other tensors that is also good for laser method and does not subject to this barrier. And it does exist. And the most promising one is what's called a small Coppersmith-Winograd tensor. So let me explicitly write down this small Coppersmith-Winograd tensor. So this is what does it look like. And I want to emphasize that when Q equals 2, this is the only tensor that is known that could potentially prove the omega equals 2 using laser method. And it is known since 1987. But the reason that we don't know whether it is actually possible is we don't know what's the border rank of the Kronecker power. And let me briefly recall what's the definition of the Kronecker power. So if I have a 3-mode tensor, I can define, if I have 2 3-mode tensors, I can define what's called the Kronecker product to be, you just take these 2 tensors, you just tensor them together and reorganize the terms such that it becomes another 3-order tensor. And for Kronecker power, this just means that you take the same tensor and you just take the Kronecker product with itself k times, and then it still becomes a 3-mode tensor. And this is what's called the Kronecker power of a tensor. So now I'm not going to tell you the details about how to implement the laser method, but I'm going to write down what's the result after implementing the laser method with a small Coppersmith-Winograd tensors. So this is the upper bound for omega that you will get if you implement the laser method using small Coppersmith-Winograd tensors. So now I want to show you some of the power of it. So it is known that the border rank of this specific tensor equals Q plus 2. So if you look at this number, so this small Coppersmith-Winograd tensor sits in the Q plus 1 dimensional vector space tensoring 3 times. So this is 1 larger than minimal border rank. And if you just plug in, so just plug in the formula when K equals 1 and Q equals 8, you can get the upper bound for omega as good as 2.41. So now if you look at this formula, you can see that if I have a good bound for the border rank of the Kronecker power, in other words, if I know that the border rank of the Kronecker power is much less than the power of the border rank of the original tensor, then I can get a better bound for the exponents. And this has been an open problem since 1987. And what is known before our results is that, so we know all the Kronecker square, or the border rank of all the Kronecker square except for Q equals 2. And we know when Q equals 2 is in between 15 and 16. And we know some results about the higher Kronecker powers, but the result that we most care is when Q equals 2. So, and I want to also say one word about how does it relate to 3×3 permanence. So in fact, if you take the Kronecker square when Q equals 2, and you do a linear change of variable, this is exactly the 3×3 permanence considered as a tensor. So let me state the main results. In fact, so this is joint work with Austin Connor and J.M. Landsberg. So we explicitly worked out the border rank of the Kronecker square when Q equals 2. So this is 16. And unfortunately, this is sort of a negative result towards advancing the exponent of matrix multiplication, because we showed that this is in fact the square of the border rank of the small Coppersmith-Winograd tensor. So although this is not such a positive result to get a better upper bound for omega, but the tools we're using, I would say that it's very interesting. We use an enhanced version of what's called border apolarity, and all the previous tools are not going to work to get such a good to get the border rank of the Kronecker square. And border apolarity is sort of a very new tool that is very powerful for computing border ranks of some special tensors. And I'm not going to tell you what are the enhanced version that we did, but instead I want to give you a broad picture of what border apolarity technique is doing and how does it incorporate the tools of modern algebraic geometry to help us compute the border rank of the tensors we care. So let me start with the notations. So I have a 3-mode tensor. Now I can look at the coordinate ring of the Secant embedding, or you can think of it as just the coordinate ring of the space of rank 1 tensors. And this coordinate ring is Z3 graded because we think A is of grading 1, 0, 0, and B star is of grading 0, 0, 1, 0, and C star is of grading 0, 0, 1. And now this is a symmetric algebra. And we can think of this symmetric algebra X on your tensors via differential operators in this way. So we think of the basis in the dual of A is acting on A by, you think, so alpha I, if alpha I is the dual of AI, we think alpha I acts on AI by taking the partial differentials with respect to AI. So this A dual acts on A and B dual acts on B. And similarly, C dual acts on C by differential operators. And for symmetric powers, we just think of it acting on A by higher order differential operators with constant coefficients. So we think of the symmetric algebra consists of all constant coefficient differential operators. So it will act on our space of tensors. So I can talk about what is called the annihilator of my tensor. So this will consist of all the differential operators in S such that this annihilates my tensor. So this is in fact an ideal, and it is in fact an ideal that defines a Gorenstein algebra with so-called degree 111. And this will be a Z3 graded ideal of S, and this can be very easily computed if you know what is your tensor T. So now what does border apolarity says? So border apolarity basically says that the border rank of your tensor is bounded above by R. This is equivalent of finding out a multi-graded ideal satisfying 3 conditions. The first condition says that my ideal lies inside this annihilator of T. This is some explicit condition that can be checked. And the second condition is the Hilbert function of the corresponding portion. It's this number. So this number basically says that its Hilbert function is always equals R if possible. So if R is less than the dimension of the ambient space, then the Hilbert function of the portion equals R. If the dimension of the ambient space is smaller, then it equals the dimension of your ambient space. And the last condition is basically the most subtle one. It says that you want your ideal to be a limit of radical ideal of R distinct points in this Secret variety. So basically, this border polarity technique translates of finding the border rank of your tensor to finding an ideal that's satisfying 3 conditions. So I want to give you some of the idea of why does this border polarity work? So basically speaking, remember if we have a border rank decomposition of my tensor, means that I can write my tensor as a limit of the sum of distinct points in your Secret variety. So this Ti is just some points in the Secret embedding. So T will be a limit of sum of R distinct points. So now I can look at the ideal of these R distinct points. So the union of these R distinct points, this is going to be a radical ideal of R distinct points in the Secret embedding when T is not 0. So to get the ideal on the right-hand side, we just take the flat limits and let T goes to 0. So the limiting ideal is exactly the desired ideal on the right-hand side that will satisfy these 3 conditions. And I want to emphasize that you don't take the limit in the Hilbert scheme, because Hilbert scheme only fix a Hilbert polynomial, but you need to take the limit in the multi-graded Hilbert scheme, which you need to fix your Hilbert function. So now I also want to spend several minutes to sort of talk about why can we fix the Hilbert function. So remember, the idea of border polarity is I take a border rank decomposition, a random one, and I look at what are the R distinct points there, and I take the ideal of those R distinct points. How do I know that these R distinct points will always give me the same Hilbert function? So I want to briefly explain that. So now I just recall that here by Hilbert function, I actually mean the Hilbert function of the quotient algebra, means that in degree STU, I'm taking the dimension of the corresponding quotient in degree STU. And now I want to explain that when you're doing the procedure, how can you ensure that your Hilbert function is fixed? So the reason is a very simple observation. It's an observation that when you take border rank decomposition, this can be very flexible. So let me use this border rank decomposition as an example. So this is a border rank 2 tensor. It is in fact of rank 3. So this is one border rank decomposition of my tensor. If you look at how we take the limit, in fact, inside the brackets, only the terms with only the constant term and the t terms matter. So all the t squared term, t cubed term does not matter inside the bracket, because when you take the limit, all those terms goes to 0. So in other words, when I choosing my rank 1 points, I can be very flexible. I can add t squared terms, t cubed terms, and other higher order t terms. So this means that I can perturb my points when choosing my border rank decomposition. So I can perturb all my rank 1 points such that, So I can perturb my rank 1 points chosen such that the rank 1 points are all in general position when t is positive. So this ensures that I can take I can fix my Hilbert function. And when I take the limit, I can also make sure that in the limit, the Hilbert function is fixed. So that's basically the reason why can you fix the Hilbert function when you want to find your candidate ideal. So let me briefly summarize what border apolarity does and what deformation can help us to implement border apolarity. So in other words, border apolarity says that in order to compute the border rank of the tensor, instead of computing the border rank of the tensor, instead, we can just find ideals satisfying several conditions. And the first condition says your ideal is inside a fixed ideal. And the second condition says that you can fix the Hilbert function of your ideal. And these two conditions, we also have some bonus if your tensor has a lot of symmetry. So if you look at your tensor, if you look at the group GLA cross GLB cross GLC, and if you look at the elements in the group that stabilize your tensor, and if this group has a large dimension, then we'll say this T has a large symmetry group. So if this is the case, we can further ask the candidate ideal to be Borel fixed. And this is in fact a very important criterion that actually will reduce the search space of our candidate ideal into something that we can handle. So these two conditions, in fact, they are all programmable polynomial conditions. And we do have programs explicitly implementing these two conditions, and you give it a tensor, then it will tell you what are the candidate ideals that satisfy these two conditions. However, the third condition is more subtle. So you want to make sure that your ideal is a limit of radical ideal of our distinct points. So this condition is very similar to asking whether a zero-dimensional scheme is smoothable or not. So we need more deformation theory tools in order to check this condition. So basically, that's the broad picture of what border apolarity is doing. So maybe I will stop here a little bit and ask if there's any questions. All right, then let me move on. So, so basically, what we plan to do in the future is that we are interested in finding the border rank of other matrix multiplication tensors. So in fact, finding explicitly the border rank is very difficult. For instance, if you look at square matrix multiplication tensors, the only known border rank is 2 by 2 matrix multiplication tensors. We know the border rank is 7. Even for 3 by 3 matrix multiplication tensors, we do not know its border rank. So using this border apolarity, we have some candidate ideals satisfying those two conditions. And then we need to check whether it's a limit of radical ideal of our distinct points or not. And in here, the main problem is that theoretically, we can compute the deformation space of that ideal. But however, this ideal is so complicated that even the largest computer we can access cannot give us not even the tangent space of the deformation space. So we need kind of more refined information and probably more refined tools from deformation theory to make us figure out whether this satisfies the last condition or not. So that's the first direction of what we plan to do in the future. And in a slightly different direction, so previously I said our result about a small Coppersmith-Winograd tensor is kind of a negative result towards the upper bound of omega. So now we have some ideas of how to get a more positive result towards the upper bound of omega. Is we look at a slightly different family of tensors. This is what we call the skew CW tensor. So it's the skew cousin of small Coppersmith-Winograd tensors. So in fact, this family of tensor has the same usage as small Coppersmith-Winograd tensors in upper bounding omega. So this is exactly the same formula as before if you apply laser method. And the only difference is that I replace this small Coppersmith-Winograd tensor by its skew cousin. So the value for those two family of tensors in laser method are exactly the same. And the reason that we hope this family might be better for upper bounding omega, and the reason is basically this tensor, the symmetry group or the stabilizer is symplectic group. However, for the original small Coppersmith-Winograd tensor, the symmetry group is orthogonal group. And as we know that the dimension of the symplectic group is larger than the dimension of the orthogonal group. So it's the skew cousin, in fact, has a large symmetry group. So we hope that this will help us in getting a smaller border rank of the tensor. And what's actually true is that if you only look at, if you do not look at the Kronecker power, this is not as good as small Coppersmith-Winograd tensor because the border rank of its skew cousin is in fact larger than the border rank of the original small Coppersmith-Winograd tensor. But the hope is still does not end, because as long as you take Kronecker square, you can see the difference. So we see that for Kronecker square of small Coppersmith-Winograd tensor, the border rank of it equals the square of the border rank of the small Coppersmith-Winograd tensor. So we sort of have no savings if we take Kronecker square. However, for its skew cousin, the situation is completely different. So when Q equals 2, if you take its Kronecker square, and if you look at the border rank, we know that the border rank of the Kronecker square is 17, which is much less than the square of the border rank of the original tensor, which is 25. And for Q equals 4, the square of the border rank when Q equals 4 is 64. And for the border rank of the Kronecker square, we have this means we have strong numerical evidence to show that this is bounded above by 42. This is just a numerical proof. And we are trying to see if this is exactly 42 using our sort of enhanced version for the Apolarity method or not. And we also plan to do a Kronecker cube because we expect that when we go to Kronecker cube, this will be the first case that we might beat the current best upper bound of the matrix multiplication exponents. So, and that's basically all I want to say today. So thank you very much for listening.
Thank you. Thank you. Let's thank Amy for a nice talk. Questions for Amy? Okay, so I have a question that may be hard to answer, but I guess I was very surprised by this conjecture that W is actually 2. Can you say anything about, any intuition about why one would think such a thing?
So I actually do not know the original reason that why computer scientists think it's true. So in fact, there is a debate between computer science community that part of them think is true and part of them think is false. And also it's because we have actually steady progress about upper bounding omega, right? We have getting like closer and closer to 2. So that's, I guess that's part of reason that they are positive about it. And the second reason is that it's very difficult to get lower bound of omega, because the only possible way of getting a lower bound that is larger than 2 is, you know, explicitly what's the border rank of matrix multiplication tensors. And this is known to be notoriously difficult. Like the only one we know is 2 by 2 matrix multiplication, and we're working on 3 by 3. So does that answer your question?
Yeah, a little bit. Thank you. Great, more questions.
Hi, Amy.
Hi.
So I think you mentioned sort of some things known about. So I'm asking about like cactus rank versus smoothable rank.
Right.
So you said sort of for cubics up to 4 variables.
Mm-hmm.
I was wondering about just like binary forms in any degree.
Oh, right. So I didn't mention that part, but this is very classical, is they are the same for all binary.
Okay, great. Thank you.
Yeah.
Great, more questions. Okay, if there are no more questions, let's thank Amy again.